Ever since Einstein came up with his theory of relativity, the world has started looking at gravity in a different way. Earlier seen as a force, gravity has since found its source in the curvature of space-time caused by supermassive celestial objects. Detected only in 2015, gravitational waves are something we know very little about. However, after years of searching, scientists are one step closer to detecting gravitational waves in space. Let's find out how. First off, enter Fermi Gamma Ray Space Telescope. Physicists sensed the gravitational waves first in 2015 on Earth using laser-based detectors, though there is still a vast majority of scientists who are also looking for gravitational waves using radio telescopes. There hasn't been much success in both cases. Up until now, only the Laser Interferometer Gravitational Wave Observatory, or LIGO in short, located in the United States of America and Virgo, Europe, have detected gravitational waves from merges of dozens of black holes and a pair of neutron stars. However, the data still turned out to be inconclusive, especially in the case of radio telescopes, and is being studied further. How frustrating, right? Anyway, the detectors in the observatory shoot lasers in long vacuum tubes ranging many kilometers. Once a gravitational wave passes through these tubes, it alters their length by a very small amount, which is detected by the lasers. However, a majority of physicists have been conservative about the efficacy of these laser-based detectors as well as the radio wave methods. They wanted a bigger thing that could look for the big mergers happening millions of light years away in distant galaxies. One of the reasons for interest in this is the fact that these mergers can only be seen or detected with the help of gravitational waves. Our conventional telescopes can't look that far into the universe. Then there is good news. Turns out Fermi Gamma Ray Space Telescope may just be the answer. A new study has revealed that the Fermi Gamma Ray Space Telescope is capable of detecting a passing gravitational wave, at least in theory. What's funnier is that they are only discovering this just now when the telescope has already been in orbit for 14 years. No doubt, with each discovery in the universe, we discover new depths of our own ignorance as humanity. Moving on, Matthew Kerr, the team leader of gamma ray studying astronomers at the Naval Research Laboratory, commented that this definitely came as a big surprise to everyone. No one had any idea that the Fermi telescope could do that when it was launched into space. Just to drop it here, Fermi Space Telescope is a spacecraft belonging to NASA, commissioned in June 2008 to detect and study the most powerful burst of energy in space, the gamma rays. Its main instrument is called the Large Area Telescope, or LAT, which was also the reason for its previous name. Anyway, it has helped scientists to perform all sky surveys, and this ability is exactly what makes it special for the detection of gravitational waves in space. For comparison, while the radio telescopes on Earth have to be pointed at cosmic bodies for a short window burst, the Fermi telescope can keep in its sight a number of objects at the same time. With this background, now let's get into the details of how Fermi would save the day. So now, coming over to the modus operandi. Before we get into the details of how Fermi would detect the gravitational waves, it's important to know what causes them and what they do. Gravitational waves are produced when two supermassive objects, such as black holes, come close enough to start orbiting each other in a spiral and ultimately collapse together. These resulting gravitational waves move through the fabric of space-time, much like if you threw a stone in a stagnant pond. But what they do is, they cause a distortion in the fabric of space-time. This distortion caused by the gravitational waves is what we can detect using the Fermi Gamma Ray Space Telescope. But doesn't the Fermi telescope just detect gamma rays? So what's going on here? Well, if you think about it, gamma rays also travel through space-time, so any distortions along their way would result in deviations in the time to reach our observatory by a gamma ray from a particular source. And since Fermi can detect those gamma rays indirectly, we'll be able to detect the gravitational waves. But there's still one problem. Many scientists agree that there aren't enough gamma rays detected by our sensors to sense the gravitational waves. Moving on, what about the gamma rays now? To confirm this thing about not enough gamma ray particles, Kerr and his fellow scientists set out to work. They pulled the 12.5 years of logs from Fermi's archives for gamma ray photons from about 30 pulsars. And fairly enough, while gamma ray photons were a rare thing, so much so that Fermi went weeks without a photon in gamma ray frequency. However, their trawl and toll through the heaps of data found enough protons to make a gamma ray pulsar timing array, or PTA. Quick thing, PTA is a set of arrival times of pulses from a collection of pulsars across the sky over many years. A slight distortion in space-time due to gravitational waves leads to variations in the PTA. So have they detected the gravitational waves? Like the rest of us, Kerr had wished the same, for certainly he'd have won his Nobel Prize for this. Unfortunately, the data from the gamma ray PTA was not able to detect gravitational waves definitively as well. These results also turned up with a signature in the background that is expected to be gravitational waves, but with too much noise to say anything conclusively. However, an interesting amazing breakthrough Kerr and his team were able to make was they were able to set an upper limit to the value of their signal. What this would be able to do is, if Fermi stays in orbit for longer, in the next 5 to 10 years, it'll have comparable sensitivity to that of radio waves PTAs. But didn't we already have radio wave PTAs, whose results were inconclusive, so why get a gamma ray PTA too, when it doesn't work either? And now, how gamma ray PTAs would prove to be useful. Although it seems like the Fermi Gamma Ray Telescope is not much of use, there are scientists which beg to differ. They are of the opinion that Fermi has a much bigger part to play in the future towards detection of gravitational waves. One such physicist is Mara McLaughlin of West Virginia University, who works in one of the radio PTA teams. She believes that while the gamma ray measuring technique has a lot to catch up on, it can still work and help in reducing the noise in radio PTAs. According to her, gamma ray data can help them understand the effect interstellar medium has on the radio waves PTA data. One advantage gamma rays hold over the other PTA data is that the gamma rays are not affected by the medium. On the other hand, these particles bend the path of radio waves and slow down some of these frequencies more than others in comparison. What then the scientists get from radio waves is a smeared out signal. The gamma rays are however different due to their high energy. They get a free pass in that they are not altered by the particles of the medium. So by comparing the data from gamma rays and that obtained from radio waves, the researchers can look for and better understand the interstellar noise. If they can differentiate the noise, they can easily get the gravitational wave's fingerprint. So in a nutshell, while the Fermi Gamma Ray Space Telescope hasn't achieved what it was meant to achieve, it has still shown scientists a new way it can be used for detection of gravitational waves. No matter how far apart that may seem, the Space Telescope is still another tool in our kit for detection of gravitational waves. And now, is it the end? Regardless of all the information we have about the universe and the different mechanisms we understand, almost all of the scientific community is sure of one thing, that the things we don't know exceed the things that we know by and large. So even if we are able to detect gravitational waves, we still have a long way to go, and there are other things to explore further. Even with the fingerprint known, there are still many hurdles along the way. Once the PTAs, both the radios and gamma rays, have been successfully used to identify the gravitational background, the scientists' next target will be the individual black hole binaries. Remember the black holes orbiting together in a spiral? Studying these binaries will ultimately lead us to better understand gravitational waves. Moreover, it'll also help the scientists know more about how these swirling massive black holes affect the galaxies nearby. This will answer many questions about the effects these waves may have on other celestial objects, especially Earth. Having done that, humanity can take a leap forward and further explore how these can be used for our own benefit. That's a wrap for this video. What do you think about the Fermi telescope being employed for the detection of gravitational waves? Let us know in the comments below. Make sure to give this video a thumbs up and subscribe to our channel for more videos like this. See you in the next one.